Okay, so today what we will do, we will continue from last time and just recap. So I think for a classical system, we discussed yesterday, if we have just 1 degree of freedom, also in general, every degree of freedom is something we will call the field. So maybe we can already use that kind of a word. For each such classical system, if we know x and its conjugate momentum, which is p, we know all observables at any time. We know all observables at all time in past and future, essentially. Now, in quantum mechanics, what we discussed yesterday, I would like to put a little bit pictorially. Pictorially, we can put it like this. That suppose we have, this is time, right? And this is some moment of time t0. There's a big algebra of observables. There's a big algebra. So x, p, x cube, x to the power 4, x squared, then xp plus ex, whatnot, and so on and so forth. We could have this enormous algebra. And if we know all the values of this algebra, let me call it A, then you can, and if you take at any time t, you will know the values of this object. So if I know the values of all these observables, all these Hermitian operators at time t, then I know all these observables at some other time, both in the past and in the future. But the only resemblance with classical mechanics is that all these observables are generated, as you can say, by this only one thing, x. X generates all these observables. Although it's not a very good word to use for various reasons, we will come to that later. It's not a Gideon, it's not a mathematically, it's not a right word I think, to call it a generator as such. But anyway, but in some loose sense, you could think of this as generates of all these observables. So if you know all of these guys at some time t naught, you know all the expectations values, then you could know the expectation values both in the past and the future. And note, this is a state independent statement. So you could think that, okay, this is not a very big surprise that all of these observables are generated by a single degree of freedom, which I call x. Why? Because after all, we know the classical world and we are simply quantizing it to get the quantum world, right? But this is a completely wrong point of view. Why? Because classical mechanics is an approximation of quantum mechanics, right? You cannot use classical mechanics to justify quantum mechanics. So one should come from the other. So if I just take it from the point of view of quantum mechanics, it's a big surprise, right? From the point of view of quantum mechanics, is indeed a big surprise that all of these observables can be generated by a single degree of freedom x. Although, yeah, in the classical world, now the correct point of view is that we can recover the classical world from the quantum world. Why? Because we know that x cube would be equal to x whole cube. xp plus px would be equal to simply xp plus px and plus order h bar plus order h bar. So all of these things that we cannot factor would be of order h bar. And therefore, we recovered the classical world from the quantum world, because then it's sufficient to know only x and p at time t, then I can know all the observables in the past and future because of this factorization property, right? So this is how we recovered the classical mechanics from quantum mechanics. But in quantum mechanics, you have this infinite algebra. And if you know all of these values at time t, we will be able to know all of the values at the past and future. So see, I have tried to make all this a very state independent statement. So I'm now looking at quantum mechanics from the point of view of algebra observables. So you might think that this is crazy point of view. Why am I doing that, right? Why on earth am I doing that? And the reason for this comes actually from quantum field theory. So even the answer to the question why these kind of things, why all of these observables are generated by a single degree of freedom x, actually comes from the fact that quantum mechanics, I would say ordinary quantum mechanics, is an approximation of quantum field theory. So look, I'm not saying that quantum mechanics is incorrect and quantum field theory is not supreme, because after all, quantum field theory has the same postulates of quantum mechanics. You are not going outside of the framework of quantum mechanics to do quantum field theory. So, but the main point is that it's a different point of view where the state becomes less important and the algebra observables become more important. Now, why this is this is a point of view. So first of all, we go to Heisenberg picture for the discussion. In the Heisenberg picture, the state psi does not evolve in time. And this is equal to the state in the Schrodinger picture. This is equal to the initial state in the Schrodinger picture, or the state that we are preparing in the Schrodinger picture. Okay. So now the point is that whatever we do in quantum field theory, sorry, if you want to think in terms of a field, suppose now you think in terms of, we know that the true thing is we have, okay, let me, so we know that Lorentz symmetry is a fundamental symmetry. Is fundamental, right? And this, so basically what I'm trying to tell you, if you want to put quantum mechanics plus special theory of relativity together, then inevitably you should have a quantum field theory framework where the algebra observables should take a bigger point of view, right? And the reason I can simply explain by a nice picture. So suppose you have some state psi, right? Again, this state is not time evolving, taking the Heisenberg point of view. And now this is, suppose you have only one space dimension, you are living in one dimensional space, and this is time, and this is space time, right? And we all know that if you look at a point in space time, it's an event, then there will be this, its past and future light cone. So all points here can be causally affected by this point, and all points here can causally affect this point, right? So any point here will be affected by this causally, and any point here can affect this point. Or anything outside the light cone is completely causally independent of whatever happens here, right? Now, suppose I have an observer somewhere and I can only access this much of space, right? So basically what I can do, I can measure all operators. So the other thing that I assume here is plus locality. So locality simply means that observations can be localized. So I have some operators. Now each of these observation or operators have two labels, one space and one time, right? So I have a set of operators that I can measure here, but I cannot measure anything here. I don't have simply access to it. Now, whenever I measure something, the state, of course, is changed, right? And it will affect my future measurements. Or I can put it this way. Suppose I can know the degree. Suppose I know the expectation values of operator of all the observables that lie here. Then how much I can know in the future and in the past, right? So because of this thing, you see that now what I will do is draw something called a causal diamond and explain to you why this diamond is important. Now look at this diamond, okay? So if I look at any point here, then its past light cone is going to intersect this segment. If I take a point here, its past light cone is going to intersect this segment, but also going to be intersected. There's also something that lies beyond. So now if anything, if I have to make a measurement here, then it's not sufficient to know all the observables here. I have to also know the observables here, right? If I want to make a measurement here. So I can predict everything that happens inside this cone if I know all the observables here, right? I can only predict all the things that are lying inside. And similarly, if I know everything that is here, so this is its causal past, meaning that if I take a point here, then its future will lie here. If I take a point here, then its future is going to lie. But if I take a point here, its future is not only here, it's also here. So anything here is going to determine this. So if I want to go back in the past, then I can only make some inferences in this region. So similarly, so this is often called the causal diamond, or this is often called the causal domain of dependence.
Sir, can you repeat the the top part? Like, what exactly does that signify?
Okay, so let me maybe draw it again and explain. So look here. Okay, this part of the space-time region. If I take a point here, right, and look at its path, so it will lie somewhere here and it's also here. So if I just tell you some events here, I will not be able to determine what is happening here completely. You should also tell me what are the expectation values here.
Right. So
if I only know the expectation values here, I would not be able to know anything here.
Okay, so that means only if we know the expectation value of the empty part as well, we can somehow predict that point.
The point is, if you know the expectation values of all the algebra observables here, you'll be able to completely predict. Okay, let us go here, right? As I said in the quantum mechanics, if you know all the expectation values of all these guys at time t0, you will be able to predict the expectation values of all of these guys at any time in the future. Okay.
Right.
So similarly here, if you know all the observables, all the expectation values of all the algebra observables here, you would be able to know only this much of. You'll be able to predict only here, not outside of this causal domain of dependence. Because if I want to make a prediction here, you have to also tell me what is happening here.
Got it. Okay.
And similarly, if I want to make an inference about the past, I can only make in this domain of dependence. So this is often called the causal domain of dependence for this reason.
Right. Got it, sir. Thank you.
Yeah. All right, then. And yeah.
How does locality play this role into this?
Yeah, the locality plays a role because attached to every space, there is a local operator, which I can measure. So there's an algebra observables. Here, the label is time, right? In this case, the label was a time. In quantum mechanics, the label would be space and time. So here, the space is not an operator. It's simply a label. The labels are operators.
Okay, sir, I got it.
Okay. So now, the basic point of view is that, so it doesn't make sense of talking of the state, right? That's what we can do in quantum field theory is say that I know some of the things here, what I can do later, and only within this causal domain of dependence, right? So there is no way we can talk of the entire state anyway, because what is this? I mean, we can only access as part of the degrees or part of the, can only make measurements in some finite space-time region. So there is no point of talking of the state as such. So we can try to think of this in a very state independent way, just like here, I thought about quantum mechanics in a sort of a state independent way. Okay. So this is a fundamental reason why these kind of way of thinking would be better. And then what would want to do is to ask the question whether this algebra observables have a nice field has a nice field representation, right? That's what we want to understand. And now I will try to give an independent reasoning why. Okay, but but I will come back to this later. Okay, I will come back to the issues of locality and causality later. But it's just to give you a feel of why did this crazy thing. Okay, why we rewrote quantum mechanics in this way. Okay, any further question?
Sir, a small clarification.
Yes, please.
So like already like in that given observable, so like we know only these many observables at that time.
Yeah.
So that means like that particular segment is only a subset of all the observables we know.
Yeah.
At that time. So within that given observables, the above cone is what we can predict, and the below cone is what we can infer.
Exactly. Yeah.
Thank you, sir. Okay, got it.
Okay. Very good. So you are all with me. So now let me then start with a little bit more rigorous definition of what is an observable. Oh,
Sir,
what happened?
sir,
Why
hello.
did we appear? Yes.
I have a question, sir. So how quantum field theory saves us in this scenario? I mean,
In what saves us from what?
like you said that I mean, if we have locality and if I mean, you said we need quantum field theory because if we include a special relativity and locality.
Well, the reason is that the quantum field theory essentially talks about is a formalism that is based on only algebra observables, not on the state.
Okay. Okay.
That's
okay.
that's a fundamental point of view of quantum field theory. So
Okay.
I think this is not what textbooks on quantum field theory tell you directly, but this is what it is. So I want to start directly from the modern point of view and just try to motivate you why this is the right way to think about it. Because first of all, I went to quantum mechanics and showed you that even ordinary quantum mechanics can be thought in this way, although that's not what we usually do.
Yeah.
And then I said that in quantum field theory, we have no choice actually. Or if you want to put special relativity and quantum mechanics together, then basically the algebra of observables is the right way to think about it anyway.
Okay.
All right, then let me go ahead. So what I would like to do first is to define what is an observable. So let me give you some kind of operational definition here, okay? An operational definition is as follows. Okay, let's try to think in this way. Suppose you want to measure something like this operator X itself, right? What will you do? So one way to do it is as follows: put the particle in quantum mechanics. So for the moment, the particle is in only one space dimension in a constant electric field. Okay, so I would say constant in an electric field, okay, in a homogeneous electric field, homogeneous electric field, which need not be constant. So in that case, the Hamiltonian would basically have whatever the Hamiltonian was, plus some Q, where Q is the charge of the particle. Maybe I should call it E, just to distinguish it from the position, and E of T times X hat, right? So this would be the Hamiltonian that I should have for the particle. And so basically, what I will do is to say that this I would call a coupling. So essentially, now this coupling could be also a function of time. It need not be a constant. It could be something that evolves with time. And and similarly, for example, what I can do, I can also, suppose if this H0 was a harmonic oscillator, I can try to do something and change its spring coupling constant, which I can call delta KT x squared, right? So basically what I'm doing here is that I'm trying to first couple the system to something through an observable. This is what I call observable. And this is what I call, or in general, an operator. And this I would call the source or coupling. So essentially what I'm doing is I'm trying to take any kind of observable. I'm just trying to, now why it is an observable? Because I can use it to do something to the system, like change its evolution or something, right? And if I want to measure, I have to do some coupling. Without a coupling, I cannot measure anything. So even act of measurement is a coupling. So I have to use some form of coupling to be able to get this, to be able to know what the how the I mean, just to be able to do something. And then I can so essentially what I call an observable is anything that can change the Hamiltonian. That can change the Hamiltonian. So definitely it should be a Hermitian operator because Hamiltonian is Hermitian. Okay, so now what I'm doing is going to do is ask the following question. And so what I'm trying to, okay, so what I will trying to do is to now tell you about the physical meaning of different things, like physical meaning of if I have two observables, say A and B, and I take a commutator like this, okay? So can I measure this commutator? For example, that is, can I do something like this? Okay, can I measure such a thing? So what kind of, what does this actually mean, right? And also I would talk about something like taking like time ordered products, and similarly. So all of these things, the question we will try to understand is, if I take products of such operators, does it correspond to anything meaningful or something that I can measure, right? And you will see that this actually has a profound thing. For example, you take a metal, I measure its electric resistivity. I take water, I measure its viscosity. Is essentially what we are doing is measuring a commutator. So this is something that I will prove today, and the first assignment will explore one example that will directly work it out, and then we will also see what are these kind of time order propagator does. So this is often called the retarded propagator or causal response function, and this is often called the time ordered or Feynman propagator, generalized Feynman propagator. So we'll try to discuss these things today. And the key thing to discuss it would be to understand the following thing. So suppose my Hamiltonian is of the form okay. So that is the most general way I can write a Hamiltonian. So I take all possible observables that can exist, and I simply turn on some coupling for them. So actually, this is what you can now physically do in many of these trapped ions, that you trap ion in a laser field, And then you can tune the interactions between the ions by, not ions, like not talking of me, sorry. I'm talking of ions. So you could tune the interaction between the ions uh, by changing the polarization and intensity of the laser field. And so you can give rise to all kinds of couplings, and they can also be time and space dependent. So you can do that now. So in general, of course, the Hamiltonian takes its form. Later in quantum field theory, will actually consider something like that, and you will see that something very remarkable is that although you can have infinite number of such couplings, if you want to understand low energy physics, only a very few number of these couplings play a role, and this is why quantum field theory becomes predictive in a way. So so often quantum field theory yeah, that's a very beautiful thing that leads to that is what we that is something that we will see later when we understand what is called the renormalization group of quantum field theory. But for the moment, we just simply take a possible point of view that suppose I have a Hamiltonian of this form where I have write it in this way. So H becomes a function of T, right? And energy is not conserved because there's an explicit time dependence. So I guess you already know this equation, the Heisenberg equation, that so basically it means that you have to only differentiate these coupling constants, right? So dH dt would simply be, of course, sum over I AI dot OI. So if I want to see how the energy is changing with time, the energy change with time, that is expectation value of H dt, would be equal to simply sum over AI dot expectation value of OI. So this is how the energy changes with time. Okay, so the energy is not constant because I'm driving the system. All right, but can somebody tell me how to solve the Schrodinger equation now? Okay, I will be going, but I would rather taking the Heisenberg point of view, but we can also write in this way that the state psi, right, psi of t would be equal to sum u t comma t naught psi t naught, and this is subjected to the Schrodinger equation of motion. Right? And which means that if I substitute this here, I get an equation now for simply the time evolution operator, which is of this form. With the boundary condition equals to identity. Because when I put t is equal to t naught, then this ut t naught should reduce to identity, right? If t is equal to t naught, the left and right hand side should agree. Therefore, u has to be identity. So basically, I get this equation for the time evolution operator. Do you know how to solve it in general? So if h was constant, it is simply to the power I by h bar minus I by h bar h times t, right? But now this h is a function of time. Do you know the solution of this? Anybody?
Sir, exponential raised to integral of h cap of dt prime like this.
Who is it? Sorry, can I know your name, please? So what is the suggestion again?
Sir, exponential raised to power iota times integral of h cap prime t prime dt prime.
I see. Is this correct? It actually, what does it actually mean? When you write this thing, what does it mean actually? Because you see that, no, this is actually incorrect. It's incorrect actually. So, and Yeah. So we will. So that's this is not correct thing. What you are doing is what you are saying is almost correct, but not quite. But yeah, you're almost there, but it is not quite. It's a bit. So the way to see it is as follows. So first, what I will do is to actually take it to. So the solution of this equation is easy to see. Should take the following form. So first, I should be able to write UTT naught is equal to identity minus I by H bar. And what you're saying is almost current, but it gives a recursive form. H T times, I'm sorry, I should have written it. Moment. So basically, you see, I kind of write it in a recursive way. And this will be a solution of this equation. So let us check it, okay? So what happens is that, so if I write this, if I take a time derivative here, I h bar del by del t of u t t naught, right? What happens on the right-hand side is that, of course, minus I times I gives 1, h bar goes away. And then I have to take this object and simply put it at time t, right? Because that's how it works. So it's indeed equal to ht u t t naught. So this is exactly what we want. So verified. So this is a solution, but this is not very useful as a solution because you see it gives you a recursive definition. So let us try to now see what it means, right? So okay, and then you see that it automatically satisfies a boundary condition when t is equal to t naught, then it has to be identity because this integral will be 0. This integral from t naught to t naught, so it is 0. All right, so let us now try to see what it means. So, so if I do it this way, so what I can do is do a little trick. I simply substitute my u t prime t naught again. So this h of t prime, but we know that u t prime t naught is 1 minus, again, I by h bar dt double prime ht double prime. Yeah, this is the problem. I'm always running out of space. 1 second. 1 minus I by h bar dt double prime ht double prime ut double prime t naught, where this is from again t naught to, but now t prime, right? All right. So now then if I see that I get the first term, which is minus 1 over h bar dt prime, and this is from t naught to t, t naught to t dt prime ht prime. That is the first term. The next term is simply plus minus I square by h bar square. Then I get dt prime dt double prime. But it's important to pay a note to this. What is the integration range here? The t double prime integral goes from t naught to t prime, and the t prime integral will go from t naught to t, right? And this would be ht prime and ht double prime. Okay, and then you could easily see that, and then like this, and you can easily see that I can write it in this way, that utt prime utt naught would be equal to sum I is equal to 0 to, or n is equal to 0 to infinity, and then I have dt1, dt2, and then dtn, where tn goes from t naught to tn minus 1, and similar Tn minus, and this, so every range will go from here, from T0 to the next one. So this will go from T0 to T1, and this will go from T0 to T, and then I will have H, T1, H, T2, and then H, Tn, right? And then there is a minus I to the power n by H bar to the power, okay, this should be inside the sum, sorry. Okay, so this is what I will have, right? If I look at this entire series. So you see that there is something very special that is happening, is that there is a time ordering. So you see that in this way, because the integration ranges, the T1 is always greater than equal to T2, T2 is always greater than equal to T3, and so on and so forth, and T3 and greater than equal to Tn. So basically there is a time ordering. So whatever has happened earlier is basically reads like Urdu. So whatever has happened earlier is going to be on the right side, and then you should read from right to left, because this is what has happened earlier, and then the next one, like that. So it is always happening. So this operates first, then that operates. Whatever is earlier will operate earlier. Whatever is later will operate later on the state. There is some kind of this. So this is called a time ordering. Okay.
Sir, we'll have a U T0, sorry, T and T0 term as well, right?
So this is the nth term, what have you written?
This is the sum over n is equal to 0 to infinity. So what was the question again? What term I missed, you said?
U of Tn comma T0.
Well, that is already taken care of. So that's exactly the point. I mean, what I'm doing is I'm going to, so when I went from here to here, so you see that here I replace this again by identity like that. So I'm going to recursively do it. So there's so many brackets here. If I unfold all the brackets, then I get this.
No, but in the
Right?
end, we'll still have one U term, right?
Well, as I said, this is a recursive definition, which means that in the end, I'm not going to have any, because I'm just going to keep unfolding this forever, and that creates the series.
Okay.
So how do you define the series of e to the power x? That also has a similar recursive definition. Right? So there,
Yeah, right,
so,
right.
yeah.
Got it.
Okay. So then what you could do is that you could actually rewrite this in a much smarter way. So let us define something called time ordering. So time ordering is simply, so I'll just define for two operators. So time ordering of AT, BT prime will be equal to AT, BT prime if T is greater than T prime, but n is equal to BT prime AT if T prime is greater than T. So this is how I define. And similarly, I can define the time ordered of arbitrary number of operators. So essentially everything should be ordered by the time, okay, by the time argument. So this is ordering prescription. Now, if I do this, then you see that if I replace everything by time ordering, then you see that now you see that T1, T2, Tn are dummy variables, right? So I can always so if I remove, so if I don't take care that there has to be some ordering, I can simply replace them with, I can replace T1 with T2. So the reason I cannot do the replacement is that if I take, for example, the second term here, which has T prime and T double prime, right? So suppose this is T prime, this is T double prime. I'm integrating over them. So, but I can only integrate over T prime. So here in this range, you see that T prime is always greater than T double prime, right? So which means that I am integrating over, I think, only this range, right? T prime is greater than equal to T double prime. So Yeah, so basically I'm integrating over this, right? Yeah, so I'm integrating only over half of this range. So what I can do here is I can do a nice trick. I can simply replace it by time ordering, and then both of these integrals go up from t naught to t, and then there has to divide it by a factor of 2. Why? Because I can always interchange t prime and t double prime with also interchanging this range, right? So because they're dummy variables. So if I also, so it's essentially what I can do, instead of integrating here, I can integrate over the whole thing. But then when I put the time ordering, it automatically cuts into either here or there. But here and here, you will get the same contributions because it's simply replacing t double prime with t prime, right? So if I replace t double prime with t prime, I get this contribution. But because it's a dummy variable, so I'm integrating over, it doesn't matter. It gives you twice the same contribution. So I have to divide by the factor of 2. Now here, if you have a general kind of thing like that, then you see that I can do factorial n kind of this kind of exchanges, and there will be factorial n such different contributions that you can have, but all of them will be same because these are all dummy variables being integrated over. But then I have to replace this thing. If I'm replacing all of these integrals from t naught to t, then I have to replace this by a time ordering symbol, right? So that's the advantage of this nice symbol, is that what I can do, then I can rewrite this utt naught in this way. This is equal to identity plus minus I to the power n by factorial n h bar to the power n. Okay, there should be a summation. Then I can write from n is equal to 0 to infinity minus I to the power n by factorial n. And then there is a dt1 to dtn. And now all of these integrations go from t naught to t, and then I have a time ordering ht1 to htn, right? And this is often also written in a shorthand notation, which is time ordered exponent of what. So what he said was correct, except that he forgot to put this time ordering here. So this is simply a shorthand for this, because what is happening here is that you see that this is basically, if I didn't have the time ordering, if I omit this time ordering, then this is exactly what our friend said. So if I just write exponent minus I dt prime ht prime, I would get exactly this, but without this time ordering symbol, right? Without this, sorry, I should. So without this time ordering symbol, if I just write the exponent, I will get this. But now I should put the time ordering symbol back, and only then I get the correct answer to utt prime, right? So this is that is what is a shorthand notation for the big series, is time ordered exponent. So often it is called time ordered exponent minus I h t. Okay, so this is a, if you want to convert this into words, you will do something like, you will say something like time ordered exponent. All right.
So if, sir, the Hamiltonian commutes with itself at different times, then the time
No,
ordering
of course
will...
not. Of course not. Because these are different operators, right? So as I said, ht is sum over ai. So these are at different times you get different operators, and these two need not commute. These need not commute here. So therefore, I have to be careful about the ordering, right? If they commuted, I wouldn't have cared about the ordering. Okay, so this is what we have. So you see that what I will do is as follows. I will draw some nice picture, maybe, to celebrate what we have learned. So now from all these things, from what I will do is as follows. I will convert every such mathematical expression into some nice picture. And like Feynman used to do, I will do the following thing. So I will, if I have something like this, A ut t prime or ut t naught B. So what I mean here, or maybe what we should, let me do the following thing. I'm sorry. Let me, okay, that was the whole point. I have to rewrite it, sorry. I rewrite it in this way. I write B ut t naught A. So what it means is as follows. This means as I start with state A, evolve and evolve from t is equal to t naught to, I should call it, say something like t1, just to distinguish it from t naught, to t is equal to t1. I evolve it from t is equal to t naught, and then ask the transition probability, the transition amplitude to state B, right? The answer is the above. So I start with some state A and evolve from time t is equal to t naught with this protocol, and then to time t is equal, and then ask what is the transition amplitude to state B. This is what I will do. This is what I have to compute, and then I can now write it in a nice way. So what I will do is I will put A here, and okay, let me explain this picture. I'll always put some diagram like this. So whenever I draw an arrow, it would mean I'm denoting this operator ut t naught. So this is t naught, this is t, and this is time. My time is flowing here. My time flows from left to right. Okay. But you see that when I'm converting or translating this diagram to a mathematical formula, everything reads like Urdu. Okay. So why? Because you see that so first of all, T naught and T1, these labels get interchanged. So first comes T naught and then comes T1, and A goes on the right instead of left, and B will go on the left. Okay, so it's completely reversed when I'm going. Sorry, maybe I can simply omit this from the moment. So you see that what should happen is the A should come here. The T naught T1 labels also get flipped from left to right, and then the B what is on the right here appears on the left there on the mathematical when I write it as a mathematical formula. So this is like an Urdu translation. Okay. Yeah, Urdu is a very nice language, by the way. Yeah. So I should always translate these mathematical diagrams to Urdu when I have to write it as a mathematical formula. That will be quite general, actually. So this is how I'm going to do. I say that I just put something here to say that I prepare some. So these vertical lines will always stand for certain states, and then they will be labeled by A, B, whatever, and this will stand for some states. So when we later go to quantum field theory and study how this kind of transition amplitudes from one set of particles to another set of particles, then actually we'll also draw similar things where these things would stand for states like Fock states, and this would stand for something we call propagators. So this will be kind of a very general way to draw things. So, okay, so this is A, UT1, UT0, T1B, and this is how it should read when I'm looking here. So here, so when I'm drawing a mathematical formula, the time will flow from right to left. When I'm drawing a picture, time will flow from left to right. Okay. Okay, just keep this in mind. And why we keep this in mind? Because now we were trying to understand the following thing. What does the commutator mean? Okay. So for that, let us try to do something like this. So suppose you have some some kind of protocol, right? All right, so no, but before that, I wanted to say something else. Sorry, even before that, I have to say something. I'm sorry, I have to first say that, because without saying that, I would not be able to say this thing. So now, if you want to compute the expectation value of an operator A of t in a certain state, suppose I want to measure, uh, 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 okay, but before that, let me make a comment maybe. So you see what I'm trying to say is that a time operator involves only the algebra of operators or all the operators in this time interval t0 to t1, right? So you can say that this is this is basically belongs to the algebra of operators in this time interval t0 to t1. So that's just an observation, just to say that there is some lower limit and upper limit, and this transition amplitude is only going to depend on what you're doing here and not what you did in the past, for example. So it's only or what you're going to do in the future. It's only something that depends here on the observations that you're doing in this, or the way you're driving the system in this time period. But now let us try to say something like this. So you prepared so suppose if you prepare, so we prepared the state as A, and we are measuring O. Suppose you're measuring the X at some position. So remember, this O is in the Schrodinger picture, right? Because this is the measurement of X. But O of t is not the same as O. O of t could be very radically different from O, but you are measuring this at time t, which lies in this interval, say t0 to t1, in this quenching protocol that, or in this evolution protocol that you have designed. So then what is expectation value of OT? OT is just the above expression. Right? And now how do we write this, right? And so we know the way to write this is as follows, that we already know the answer is that A should be equal to, so this should be equal to, in the Schrodinger picture, this should be equal to A at time t, O A at time t, right? Which is equal to definitely A, and then U dagger t t naught, or t1, or yeah, t t naught, O U t t naught, A, right? And this is, so what we are doing pictorially here, let us try to convert it to a picture. And this picture looks a little weird. It will look something like this. This is A, this is A. And this is sometime t1, this is sometime t0, and then you put an operator. First let me, okay, I have to make this picture, I have to first cross some other picture. Let me first put this as t. Sorry. How do I undo? Okay, very good. Yeah. So I will put an operator insertion O. So what is happening here is that you see that this operator is inserted at time t, and this, I'm sorry, I should put the arrow this way. This arrow will stand for U t t naught, and this backwards arrow will stand for U dagger t t naught. So basically what you're doing is you're first evolving forward in time in this way, then you're making some insertion of some operator, and then you're going back in time, and then you're computing the expectation value. So where this O hat is a standard operator. So if you have to make a measurement of O at time t in this way, one way of thinking about this in a pictorial way is as follows. That's, I'm just writing the Heisenberg picture in a pictorial way, right? And this is what Keldysh and Schwinger did, and this is often known as the Schwinger-Keldysh contour. The Schwinger and Keldysh found this nice way to think about this Heisenberg picture. And so basically there's a different thing. So you see, when I was computing here, there was only, time was only flowing one way. There was no backward time contour. And this was essentially has to do with the fact that we are computing a transition amplitude, right? Whereas here, we are computing an expectation value. Whenever we compute expectation value, you have to first evolve forward in time and then go backward in time, right? So this is what it is. But now you see that you could actually do something more, is that, okay, suppose so first of all, I have to give you an exercise from here. So we define this time evolution operator here, right? It is simply time ordered exponent of minus I dt prime ht prime. So exactly what our friend said, except there should be time ordering. And now you can try to prove the following, thing. So one is that u t prime and u t prime t double prime is equal to u t double prime. So this is some exercise. You can try to prove it. So there's a group transformation law, and then of course ut t prime and ut prime t is equal to simply identity, which implies that since this is a unitary operator, u dagger t prime is nothing but u t prime t, right? So basically, instead of writing it as u dagger t naught, I could also rewrite it as u t naught t. So basically, that is why this backward time arrow is justified. So what I'm doing at first, going forward in time, then going backward in time. So from what I will do something later, you would see that you will be able to easily prove this. So try to do this exercise. And before we come to the next class on your own, right? So, and I will start by asking who has been able to do it. So this is the first exercise for you. And if you're able to show this, then obviously this follows, because the second one follows from the first one, because this is ut comma t, which has to be identity, which I already showed. That's how it works. All right, so this is the thing. So now we are now we can actually take this picture and do it in another way. So let us try to see the following thing. We had A here and A here, right? And there was some operator O insertion at some point. And then what you could do, you can actually go a bit more forward in time, say up to say T1, and you can also come back. But now you do not do any operator insertion. You simply come back, right? So up to this point, T, right? So now what you're pictorially doing, right? If you want to convert this into a mathematical formula, what you're doing is as follows. You are doing A, and then this part will be u t naught t. I'm reading like Urdu. And then from T, I'm going to T1, ut T1. And then I'm going back from T1 to T naught. Sorry, let me do it slowly. So this was A. I start from here, then I go. I'm sorry. Yeah. So first I'm doing this. I'm going from T naught to T, and right, and then I'm going from T1 to T, from T to T1, and then I'm going back from T1 and back to T naught, and then I'm completing this. So first I'm going from T0 to T, and here crucially I should insert the operator, which I forgot, sorry. Let me then maybe I should write it again, this part. O of T, and then I'm using going from T to T1. Sorry, this is simply O because there is no, sorry, simply O itself, not the OT1, simply O operator. And then I have U, but this is my usual operator O, right? This is what I want to intend to measure. And then I go from T to T1. And then I go back from T1 to T0. And then I again complete with A, right? This is what am I doing here. All right, is this clear? Is this clear that this, how I converted this to this? If you have not, then ask me. But you see that this part I can rewrite as U T1 to T, right? And this is T1 to T0, right? So you see that this. So what am I doing here is, you see that I'm going from T to T1 and T1 to T0. But then these part and these part actually cancel out because there is no operator insertion here. So these actually cancel out. And so this is actually equal to, so this part is actually equal to, so again, by the composition rule, this has to be equal to T T0. So this part will be actually equal to simply U T0 T, which is exactly what I wrote earlier here, right? What I wrote earlier here. So this is equal to nothing but again A OT A, because this part is equal to U T0 T, which is equal to U dagger T T0. All right. So you see this, so basically I can always go forward and backward, and anywhere where I do not insert operators, they're going to cancel out. That part of the two contours are going to cancel out. So actually what I can do, I can actually, sometimes what people do is simply stretch it to infinity and insert an operator here and just simply go back without inserting any operator. That is how I measure a 1-point function. So that's the measurement. So I can actually represent it pictorially like this. And this is something that's going to be useful for us later. Okay, so just keep this in mind. So this is a very nice way to like represent it by a nice diagram, what we're actually doing in terms of operators. Okay, so now let me try to tell you what is this meaning of this AT BT prime. Okay, so to show this, what I need to do is as follows. Suppose I have my Hamiltonian HT, which is something that I already decided, AITO. But what I do is that I do something like a, so this is my H, what I should call it as H tilde, which means the new Hamiltonian. I make a small perturbation to this. I make a small perturbation to this Hamiltonian, and this I do by the operator B. So what I do is I put a small g t times B. So this is what I can call delta H, and this was my original H. So what am I doing is I'm perturbing my Hamiltonian with something, and typically what g of t would be is localized. G of t would be a delta of t minus some t1. So times some constant g0. So what I want to do, I want to make a sharp some kind of change in my Hamiltonian, and that would be only at time t1. I give some peak with some constant electric field. For example, I could do it like this. I can B could be equal to the operator x, and then g of t could be some electric field E0 delta t minus T0. So what it means is that I simply just give a short pulse of with an electric field which is homogeneous, and I immediately turn off. So it's like a pulse. So if you want, you could make it like a narrow Gaussian pulse. So basically what I do, this is often called the pulse probe. Okay, this is often called the what is called the pump probe spectroscopy in a way. So what you're doing is you are basically giving a short pulse to your evolution protocol, whatever your evolution protocol is. And now what I'm going to do, I'm going to measure let's skip this picture. Sorry. I will measure A at time t2. So I will make the measurement of the operator A at time t2. Now, because I have given this extra pulse or extra thing, what my expectation value of A at time t2 will change, right? Because my Hamiltonian has changed, right? So the question is, what is delta A? I'm sorry. That is, what I'm asking is the difference A when I'm evolution with H tilde minus expectation value of A at time t2, but evolution with H. So there are two Hamiltonians which differ by this extra term, and I want to compute what is expectation value of the measurement A at time t2 that is going to, that I will have, and what's the change in the expectation value because of this new protocol, which is slightly different from the earlier one. Okay, so that's the question. The question should be here. All right. So is the question clear? If not, let me please ask.